The title of this set of notes is Limits, and the outcome is that you will be able to evaluate limits graphically, algebraically, and numerically. One of the first things we're going to talk about is a rate of change. And you might remember from algebra that a rate of change is just a slope. So here, if I have this graph, if I wanted to know the rate of change between any 2 points, I could do that just by picking 2 points and drawing that line there and finding its slope. So the slope would be the average rate of change between those 2 points. And just as a reminder, your slope formula, if this is the first point, we call those coordinates x1, y1. And the second point has an x2 and a y2. And so the slope would be the change in the y. So how far does it rise versus the changes in the x? How far does it run? So that would give me an average rate of change. But what if I wanted to know the rate of change at an exact moment? That's called the instantaneous rate of change. It would be the slope of a line that just touches that one point. You notice that line there is tangent. If I could know the slope of that line, I could know the instantaneous rate of change. The only problem is that I only know 1 point, and I need 2 points to make slope. So what we're going to do is we're just going to make 2 points that are really, 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 really close together. And if those 2 points are really, really, really close together, they're practically the same point. It's practically a tangent line. So I'm going to call this point, this coordinate x, and I'm going to pick something that is so close to x that it's just a little bit away. And I'm going to call that little bit amount h. So this point, this red point, it's on the orange graph. Its x-coordinate is x plus h. So x plus just a tiny bit more. H is very, very small. So if I do that, and I use my slope formula, then the y-coordinate, the second y-coordinate, is the output at x plus h. And the first y-coordinate is the output at x. So that's y2 and y1. The second x-coordinate was x plus h. And the first x-coordinate was x. And you might notice that in this equation, my denominator, that I have x minus x that cancels out. So I have, for my instantaneous rate of change, I have this formula, f of x plus h minus f of x all over h. And we're going to notate that with, that is the change in the y values. The delta means the change in, over the change in the x values, which in this case we're talking about things happening over time because we're talking about a speed. That's it for rates of change. So now we're going to talk about limits. So there's 3 ways that we need to know how to evaluate limits. So the first method I'm going to show you is graphically. So when you're looking at this graph, we're going to focus on what's happening at 1. So the first question is, what's happening as x approaches 1 from the left? That minus sign means from the left. So I'm going to come in from the left of my graph, and I'm going to approach 1. And I see that my function is approaching -1. So I would say the way to read this is that the limit as x approaches 1 from the left of f of x is -1. So each of those symbols translates into English. Similarly, I want to know what is the limit as x approaches 1. So I'm going to come in from the right side of the graph towards x is 1, and I see that my output is +1. So what is the limit as f of x approaches 1, just in general, neither from the left or the right? These two are different, so there really is no limit. It doesn't approach anything at 1. It approaches one thing from the left, one thing from the right, so it doesn't really approach anything from both sides. So it's actually non-existent. We say it does not exist. And you can write D&E. On the AP exam, they use the word non-existent. Last question, what is f of 1? Does f of 1 exist? Right here, f of 1 is shaded in. We say that when the input is 1, the output on this graph is 0. Next, we're going to look at evaluating a limit numerically. So numerically means when you have a table of values. So it says use the table of values to find the value of the limit as x approaches 2 of the function x minus 2 over x squared minus 4. So you might notice that if I just plugged 2 in and said, hey, what does this thing look like at 2? I would get 0 over 0. And that means nothing to me. It's not equal to 1, it's not equal to 0, it's not equal to infinity. This is actually called the indeterminate form. It determines nothing. Indeterminate. I'm going to write that again so you can see the spelling. Indeterminate. Like undetermined, basically. So I have no idea what's happening. I do know the graph is undefined there. But it could still have a limit, even though it's undefined. And so what we're going to do is we're going to look to the right and to the left of 2, because you guys saw in the last one that as long as it's approaching the same place from the right and the left, it'll have a limit. So I'm actually going to go to the bottom of the table, and I'm going to figure out what does this function equal when I plug in 2.1. And this is where I'm going to go to my calculator. So on my calculator, I'm going to go ahead and put the function in. So my numerator is x minus 2, and my denominator is x squared minus 4. Just want to double check that I have that right. I dropped the 4. Okay, so I want to know what this thing equals when I input 2.1, because that's a little bit to the right of 2. So I am going to go to my table. You notice my table's in increments of integers right now. So I'm going to go to table set, second table set. And I'm actually going to tell the calculator to ask me what I want for an x value. So now when I go to my table, I can type in 2.1 and I get 0.2439. Then what I'm going to do is I want to get even closer. And we're going to go by powers of 10. So we're not going to go halfway between. We're going to just put a 0 in there. 2.01. Now I see I'm at 0.24938. And you should be recording all of this into your notes. And then 0.24994. So I can see here that all these numbers are rounding to 0.25 as I come in from the right. I want to check the other side, though, the left. So to the left of 2 is 1.9. And then I want to get even closer, so I'm going to go 1.9. And then again, I'm going to go 1.999. And I can see that I'm also approaching 0.25. So that is enough information for me to say that the limit here is 0.25. The last method, and the most important method, is that you have to find limits algebraically. And the key here is to be very clever. I'm going to show you a lot of techniques. And the techniques I've listed are in the order that you should approach. So the very first technique is direct substitution. Whenever possible, you should just plug the number in. So in this example, we want the limit as x approaches 1. So we're going to go ahead and just plug in 1 for x. So we get 1 squared plus 1 plus 2 over 1 plus 1. And then simplifying, we get 4 over 2, which equals 2. And that is the limit. You always want to try direct substitution because it's the easiest and it's fantastic when it works. However, there will be times that it does not work. If it does not work, you should check to see if you can factor. So here we have the limit as x approaches -3. So first thing I should do is I should try my direct substitution because it's always the easiest method. So -3 squared plus -3 minus 6 over -3 plus 3. So this is going to give me 9 minus 3, which is 6, minus 6 is 0, over 0. There's that indeterminate form. That is a broken limit. You need to fix it. So one technique here is to try factoring. So at the top we have a quadratic. So I'm looking for numbers that multiply to -6 and add to +1. So I think x plus 3 and x minus 2. And then the denominator is x plus 3. And what you'll notice here is that you have this factor x plus 3, that it's occurring in both of them. X plus 3 over x plus 3 is equivalent to 1. So you can remove that factor. So now you're left with x minus 2. You can plug negative 3 into that. So negative 3 minus 2 is negative 5. So the limit here is negative 5. So when direct substitution fails, look to see if you can factor. You can remove your factor and find your limit that way. Sometimes you have something that won't factor, usually has a square root. You can try rationalizing whenever you see a square root. So to rationalize, you want to multiply the numerator and the denominator by the same thing, because that's just a clever form of 1. So what I'm going to do is I'm going to multiply that radicals in the numerator. I'm going to copy the numerator, but I'm going to change the sign from minus to plus. Got to do it in both the numerator and the denominator. Move that stuff down. We'll need that later. So the numerator, go ahead and FOIL that out. Radical x plus 1 times radical x plus 1 is just x plus 1. And then the outside, 1 times a radical is the radical. And then the inside, negative 1 times a radical. And then the last, negative 1 times positive 1 is negative 1. And because all you did was change the sign, what's going to happen is those middle terms will cancel out. And then I have plus 1 minus 1 also cancels out. So the numerator is now equivalent to x. And then our denominator is x times the square root of x plus 1 plus 1. So this green function is equivalent to that original black function. Now let's try our substitution. So we want to know the limit as x approaches 0. So now let's try plugging 0 in. So we get 0 over okay, so I can see here I'm going to have 0 times in the denominator. I'm going to have 0, 0. So I'm still stuck here. Still got something indeterminate. So I've got to turn to my clever algebra. Let's go back to this green function. Do you notice that there's an x in the numerator and an x in the denominator? They factor out. That's why factoring is one of our techniques. So we can cancel out an x in the numerator and an x in the denominator. And now our function is 1 over this stuff. Now let's try direct substitution. So putting the 0 in, we get 1 over the square root of 0 plus 1 plus 1. This is 1. The square root of 1 is 1 plus 1 is 2. So between rationalization and factoring, we were able to get that the limit is 1/2. The next type of function that I want to look at is a piecewise function. So how do you find the limit? I'm going to move all that stuff down. Of a piecewise function. The first one, A, it says, what's the limit as y approaches 6? Well, 6 is greater than negative 2. So I'm just going to use direct substitution here into this branch. That's not bad at all. What about the limit as y approaches negative 2? While it's true that negative 2 goes into this branch, notice that negative 2 is where the two branches meet. So the graph might be doing something different on the left and the right side. And like we saw in the first example, we've got to compare the left and the right. So when you're at a break point, you need to compare the left and the right. So the limit from the right side would use the second branch. And go ahead and plug in -2. And we get 1 plus 6, which is 7. You also need to consider the limit from the left. A number to the left of -2 might be -2.01. That's a number that's less than -2, so you're going to use the top branch. -2 quantity squared is 4, plus 5 is 9. Notice that the limits on the left and the right don't match, so the answer is that the limit does not exist. It is non-existent because the left and right don't match. Right, the last type of algebraic manipulation that I'm going to show you is the absolute value function. So how do you evaluate when you have an absolute value thrown in there? The key to an absolute value function is remembering that you can rewrite an absolute value function like a piecewise function. Look at just that denominator, the absolute value of x. If x is positive, that thing looks like x. If x is negative, that thing looks like -x. So we're going to separate this into two different functions. On the right of 0, this function looks like x squared over x. On the left of 0, this thing looks like x squared over -x, because on the left side of 0, the absolute value function follows the rule -x. So now we're going to do our direct substitution. If I put 0 in here, in both of those, I will get 0 squared over 0, which is 0 over 0. It's indeterminate. So now I need to start trying some techniques. Try factoring. Notice that x squared divided by x, I can factor out an x, and it leaves me an x. So now I'm going to use this function here. The limit as x approaches 0 of x from the right is 0. Same thing down here. Before I do anything, notice that I can factor an x from each one. Now I can substitute. When I substitute 0 in from the left, I get 0 over -1, which equals 0. You can divide 0 by a number, and you get 0. Both in the left and the right limits are the same. They're both 0. So the limit does exist. It equals 0. So to end this, I'm going to have you try one problem. It's okay if you don't know how to do it. What I want you to try is I want you to try to show the work to evaluate the limit as x approaches 3 of 3 minus x over x squared minus 9. I'm going to go ahead and tell you the answer is -1/6. So see if you can figure out how to get to that answer. And we're going to start in class by looking at this problem together.